All right, so guys, again, I know that it's odd that I had you grab your notes from last time. But the reason that I wanted you to grab your notes from last time is actually, and this sounds kind of crazy, remember how long a day it was last time when we flipped the water around and we basically ran out of time in class? Well, guys, it turned of equilibrium, we used to teach in one big day. So we got done with the tube flippy thing and we would immediately jump into this and do the math of equilibrium, and the homework assignment that we just looked at was actually twice as long because it also included the math of equilibrium. And then we realized we were just trying to cover too much too fast, and so we decided to break it apart. So guys, with that said, what I want you to do is actually go here with me all the way to the top of your notes. So we need to come back and revisit where we were, because literally this is an extension of what we did last time. But guys, we're going to touch here really quickly. We're going to review for a minute, make sure that you're good on some of the questions that were in the homework. Then guys, we're going to remind ourselves about this 70-30 ratio. And then guys, that's what we're going to talk about for the rest of the day, is this product to reactant ratio that exists in these equilibrium systems. And then guys, frankly, you're going to get your homework done today. It's not a very big assignment, and this is only going to take us about 20 or 25 minutes. So you guys ready to go? Okay, so guys, let's do this first. So if you remember, this was the page of notes that you had in front of you as we were flipping the water back and forth. And guys, if you remember, we came to that magic point where the amount of water inside the cylinder stopped changing and the amount of water in the tubes became equal as we were moving the water back and forth. And guys, these are the important things that we said about equilibrium. So guys, I know these answers are in your notes, but these have got to be understandings that you possess, not just words on paper. So guys, when we are at equilibrium, what is equal? So not the ratio of products to reactants. That was 70-30. So guys, when we're at equilibrium, what is equal? The rates. And guys, what in our demonstration was representative of rate? The amount of water where? In the tubes, not the cylinders, in the tubes. Remember, we got to that point where we were moving the same amount of water forward as backward, and that was the point where we reached equilibrium. So guys, when you're at equilibrium, the forward and reverse rates are equal. If that's not something that's jumping off the page at you, guys, I would do something to make your brain go, I need to know that, because you're going to see that on the test as well. That's foundational information. So guys, when a system is at equilibrium, same amount of stuff forward as backwards at the same time. Now guys, when that happens, something else really unusual takes place. So as we started moving the same amount of stuff forward as backward, when the rates became equal, what did that then do to the amount of water inside the tubes? They became 70-30, and did they change? No, they stayed there. And guys, that is representative of concentration. That when we hit equilibrium, the amount or the concentration of reactants and products stops changing. And of course that makes sense because we're moving the same amount of stuff forward as backward, and as a result things stop changing. And as we said last time with our tubes, that happened at a 7-3 ratio, and it stayed there no matter what. Guys, any questions about this? Because it's all review of the concepts of equilibrium. You okay? So guys, let me ask you a question then. Did it really stay at 7-3? Remember what we started doing? And we started adding and removing liquids from the tubes? And did it stay 70-30 when we allowed it to come back to equilibrium? Not 70-30, but it did go back to 7-3. Guys, this ratio, 7-3, for that system does not change. And you can add or subtract, and guys, it will always go back to that 7-3 ratio. And that's the whole point with Le Chatelier's principle, is it allowed us to figure out if we change something, what direction does the reaction go to get back to Le Chatelier's, to get back to equilibrium. And that's Le Chatelier's principle. That's what it allows us to figure out. So guys, let's pause again. What questions do you have about all of this stuff? Because these are the important nuggets relative to equilibrium. Rate, concentration, and predicting shifts relative to Le Chatelier's principle. You guys good? Okay, so guys, here's then what we're going to do for today. We're actually going to talk about this 7-3 ratio. Because guys, I think we talked last time in class about the idea that all reactions have a product to reactant ratio, but it's not always 7-3, but we can look them up. And guys, this is where you need to now start taking notes, because we're now going to dig deeper into this idea of the 7-3 ratio. So guys, jump all the way to the bottom of your notes, flip your page over if that's where you're at, and now we're going to talk about this relationship. So guys, I would do this first, this subtitle here, make this the next heading in your notes. So guys, what we're going to talk about today are what are called K sub C. So guys, with that said, don't write this down, because you don't need to know this in word form, but let me give it to you. So guys, all that an equilibrium expression is a mathematical ratio of products to reactants when a reaction is at equilibrium. But guys, remember in math, when we talk about ratios, we're talking about fractions, and so this is what you need to write down. This is the expression for Kc. So Kc is equal to, and then guys, the numerator of the fraction is the concentration of products. And then the denominator, bless you, the denominator of the fraction is the concentration, obviously, of reactants. But guys, this creates a problem, because remember, these are reversible reactions, which means they're going both directions at the same time. So the reactants turn into products, but then the products turn back into reactants, and both the products and reactants perform both functions. And so guys, as a result, we've got to say this. We're going to call it right divided by left. And then guys, if you don't remember the brackets, just like in pH calculations, mean molarity. So guys, this is now the general form of the equations that we're going to be solving relative to equilibrium. These are what are called Kc calculations. It's the concentration of the products divided by the concentration of the reactants. We're going to say products are always on the right, reactants are always on the left. And remember, the brackets mean molarity. You guys all caught up? Okay, so guys, normally at this point, I would show you how to take an equilibrium process, and I would give you the general form of writing Kc expressions, because guys, there are some rules to this. But rather than give you the rules, I'm going to show you an example and let you come up with the rules. So guys, don't write this down, but I will ask you to write down the rules. So guys, it goes like this. Let this soak in for a second. So guys, we've got BF3, we've got water, we've got H3BO3, and then we've got HBF4. So this is our balanced equation. It is actually balanced 4-3 to 1-3. But guys, what I want to do is I want to show you the product to reactant ratio for this, the Kc, and see if you can come up with the rules for how to write Kcs. So guys, first of all, the right side is going to be on top. So the right side is now properly written on top, and then the left side is now properly written on the bottom. So guys, let me give you a second to compare the balanced equation with the Kc expression, and then see if you can come up with the two rules about how to write Kc expressions. Uh-oh. What just happened? Oh, beach ball of death. We're okay. So guys, let's talk rules. So based upon this balanced equation, and then looking at how it changed to become the KC expression, first of all, notice this. The right side is on top because we knew that from here. But guys, when you write KC expressions, what are the changes that you make when you take the things from the reaction and turn it into the ratio? What changed? Go ahead. Yes. 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 Good. Guys, that's rule number 1. Can we write it down? And then I'll show you. Well, let me show you first. So guys, notice this coefficient. That's this number. Guys, notice this coefficient. That would be this number. And then this coefficient would be that number. So guys, what do we do with coefficients when we write them in the KC expressions? They become exponents. Rule number 1 is this. Coefficients become exponents. I would write that down. You might consider writing down rules, and then rule number 1 is this. Coefficients become exponents. But guys, there's a second change that you have to make, and it's a little more subtle because it's implied but not directly represented. It's a mathematical thing. Does anyone see it? Guys, what happens to these additions when you put them down in the function? They become multiplication. And you guys understand that, right? If you've got two things in parentheses with no sign between, it's understood to be a multiplication. So guys, when you're writing your KC values, your additions become multiplications. That's number 2. So your 2 rules for writing KC expressions are 1, your coefficients become exponents, and then number 2, your additions become multiplications. And guys, if you can keep track of that, and if you can remember that it's right divided by left, you're going to do really well with these. So guys, what we're going to do is this. We're going to solve 2 of these, and then guys, you're going to have the remainder of the day today to work on your homework. You'll see, you're going to have a lot of time to work on homework. So, you guys ready to try a couple of these? Okay, so guys, this is the way this is going to go. You will be given a balanced equation. You will write the KC value for the balanced equation. Then you'll be given some data that you'll plug into that, and you'll solve for whatever you're not given. So 2 examples. Here comes number 1. Scratch the balanced equation into your notes. Now guys, what you're going to see as I solve this is I'm going to be jumping around on the screen a fair bit. And I'll guide you through. Well, you know what? Better than that, let's do this. Don't jump around and be careful of what you write down. And I'll just tell you, you don't need to worry about writing this down. So let's just, you guys will just continue straight down. So guys, now that you've got the balanced equation, the first thing that we've got to do is write the KC expression. Guys, don't skip lines. Put your KC expression right below the balanced equation. Bless you. Is there another round of sickness going around? It's crazy. My daughter had this girl come over Saturday night to have dinner with us, one of our neighbor friends. She's like hacking and coughing. She couldn't even swallow dinner because her throat hurt so bad. Like, why are you in my house? Go away. You're going to get us all sick. It was not good. So, guys, here's what I want you to do. You didn't skip lines, right? You're up here. Guys, write the KC expression. Remember, there's 2 rules. Coefficients become exponents. Addition becomes multiplication. You know that it's right over left. Guys, based on that, give it your best shot at writing the KC expression for this equilibrium system. Remember, it's brackets and not parentheses. And guys, that does matter. Brackets and not parentheses. So guys, you take a swing at it. Then I'll show you the answer. Then I'll give you some data. Then we'll solve for KC. Then we'll talk about what that means. Then we'll solve one more, and then you'll have time to work on homework. You guys ready to go? Okay, so what goes on top? The right or the left? The right. What do we do with the 2 that's in front of the SO3? Did it look like this? And you put it in brackets, right? Because that matters. Okay, now guys, in the denominator, we've got SO2 squared, and then we've got O2 with no exponent. And what do we do with the addition? Does it look like that? Beautiful. Okay, so now guys, all we need to do to solve this is we need some data. And so guys, in this class, we will not be gathering this data in lab. This is not a lab that we're going to do. We actually do these labs in AP, where we go and measure the concentrations of all of these things. By the way, how on earth would we measure the concentrations of these things? The answer is really cool. We shine light through the solutions, and the more concentrated the solution is, the less light that gets through. And we can actually measure the concentration based on the amount of light that gets through. Anyway, but guys, in here, you'll be given these concentrations, and you'll solve for KC. So guys, please do not write this down, but this is the idea. It says this: if the final concentrations in this reaction at equilibrium are boom and boom and boom, what is KC for the reaction? So guys, what are we going to do with these numbers? Plug them in. So guys, do it with me. KC is equal to, in the numerator, we need the concentration of SO3. So all you got to do is find it in the information that you're given. And guys, SO3 has a concentration of 0.20 molar. But guys, do not forget that that's squared. Then guys, in the denominator, we need the molarities of our reactants. The SO2 has a molarity of 0.125 molar. Again, that's squared. And then the molarity of the oxygen is 0.11 molar, and that has no exponent because there's a 1 in the balanced equation. So guys, now the only tricky bit is figuring out how to get your calculator to spit out the correct answer, which is 23. So guys, grab your calculators and poke and poke and poke until your calculator says 23. By the way, if you're not getting 23, my strong advice to you would be hit enter every chance you get, especially if you're on a TI graphing calculator. But guys, you'll know you got this right when you get 23. Has everybody made peace with their calculators? And guys, you understand that if you don't feel comfortable with your squared key on your calculator, all you've got to do is take 0.2 and multiply it by itself. So you could just do 0.2 times 0.2 divided by 0.125 divided by 0.125 divided by 0.11. That's all the squareds mean, is that there's 2 of them. And in either case, you should get 23. Yeah? I don't know. There's probably a decimal. 23.27. But realize we've got 2 significant digits, so we only get 2 in the answer. Yeah. So 23.27? Is that from the concentrations? So 4 significant digits, the numerator's got 2, and then the denominator's got 3 and 2. So we're limited to 2 significant digits. It's always the fewest. So guys, are we okay on the math? Then guys, let's talk about 2 other important things, and this stuff you need to write down. First of all, this. Guys, when you wrote down the number 23 and then stopped, I hope it just felt wrong. Why? No units. Guys, by now in this class, you've learned that you seldom write down numbers without units. So guys, the question is 23 what? And the answer is there are no units. Guys, so if you're that person that misses points on all of your labs and all of your tests because you don't put units on your numbers, you're finally right. This is the day you've been waiting for. You're not going to miss any points because that number doesn't have units. This is what is called the dimensionless number. But guys, don't confuse no units with no meaning. 23 what? Guys, interpret what you just did. What does the number 23 mean? Well, to figure it out, where did it come from? And, okay, so it's a ratio of what? Go back and look in your notes if you're not sure. A ratio of what? Products to reactants. So guys, what does it mean if this number is 23? What that means, guys, is at equilibrium, you've got 23 times more product than you do reactant, because the numerator is the products and the denominator is the reactants. And if you get the number 23, that is actually 23 over 1. So that means at equilibrium, you'll have 23 times more product than reactant. Just like in our tube thing, we got 7 divided by 3. This would be 23 divided by 1. You would have 23 times more product than you do reactant at equilibrium. Just like the 7:3 ratio, it would just be 23 to 1. Does that make sense? Okay, so guys, that then means that we can interpret Kc values. And guys, it goes like this. I would write this down at the bottom of your notes. Guys, it means this. Kc values that are bigger than 1 tell you that you have more product at equilibrium. So if Kc is bigger than 1, remember the alligator eats the big number. Guys, if Kc is bigger than 1, that means that you've got more product than reactant. Now guys, what if Kc is less than 1? The opposite, more reactant than product. But guys, notice less than 1 does not mean negative. Not less than 0, less than 1. So guys, if Kc is less than 1, again, not negative, not less than 0, but if Kc is less than 1, that means you have more reactant than product. Now guys, you ready for the bonus trivia question? Can Kc ever be negative? Can Kc ever be negative? That's the point, right? Guys, in order for Kc to be negative, one of your molarities would have to be negative. And that's impossible. You can't have a negative concentration. You can't have less than none. So guys, the Kc will never be negative because your molarities will never be negative. You guys get the idea? Any questions on the math or the concepts of what Kc values mean? We're going to solve one more and call it a day. So guys, it goes like this. Last one. Here's your balanced equation. A simple decomposition reaction. So guys, write the Kc expression. Do it beneath this. Write the Kc. When we're done with this, you're going to have time to work on your homework. Yeah. Yep. Yeah, you'll see, Caitlin, the way that I'm presenting these to you, I'm trying to do it so you can write the Kc expression first and then solve it. So I'm not giving you all the information yet because I want you to focus on one and then the next. But in the homework, it'll just give it all to you at once. So guys, you done? Did you get this in the numerator? Check and be sure. There are no exponents. It balances with ones on the product side. But guys, realize the addition becomes multiplication. If you get these wrong on the test, many, many times it's because people add rather than multiply. So good on the numerator, Let's look at the denominator. Guys, that would be HI squared. But now, guys, I'm going to throw you a little bit of a curveball. Instead of giving you the molarities and have us solve for Kc, I'm going to give you Kc, and we're going to solve for molarity. Don't write it down, but it says this. It says if the Kc for this reaction is 0.39. Guys, what does that mean that the Kc is 0.39? More product or more reactant? More reactant. It's less than 1. So guys, the Kc for this is 0.39, and the final concentrations of H2 and I2 are boom and boom. What is the concentration of HI? So guys, let's plug it in. We know Kc, 0.39. Now guys, we know the concentration of H2. It's 0.20. We know the concentration of I2. It's 0.18. And then our concentration of HI becomes our X. But what mistake are you going to avoid when you write that down? Don't forget the squared. Okay, so guys, tipping our hats to the algebra gods, how do we solve this for X? What are we going to do to solve this thing for X? First thing we're going to do is we're going to multiply both sides by X squared. I learned that as cross multiplying. I don't know if you're taught that anymore. But multiply both sides by X squared. On the left, you get 0.39X squared. On the right, it cancels. But then, guys, I'm going to be efficient about this. And the other thing I'm going to do is multiply 0.2 times 0.18, and I get 0.036. Now, guys, what do we do to solve this for X? Divide by 0.39, and we get X squared is equal to 0.092. Then, guys, to solve this for X, then we take the square root, and X is equal to, what do we get? 0.3. Does that number have units? Yes, because you're not solving for Kc. Guys, we're solving for the denominator, which is what? A concentration. It's a molarity, and the concentration, guys, is 0.30. Watch significant digits. 0.30 molar. How you guys doing? You okay? I'm good. Guys, any questions? Okay, so guys, do this. Grab your homework packets. Are we on assignment 4 or 3? 4? 4. Guys, look at assignment number 4, and I want to show you something really quickly. So you'll notice in this assignment, you're given a lot of the balanced equations. And guys, in 1D, you're given this. And guys, I want to explain to you what this is, because you've never seen this before. So guys, what on earth does CuSO4.5H2O mean? It doesn't. Guys, this is actually that compound. You may remember this from the stations activity that we did. Guys, this is actually what is called copper 2 sulfate pentahydrate. Penta means 5. So guys, let me explain to you what this thing on the board is talking about so you understand how to handle this. So guys, what does copper 2 sulfate pentahydrate look like? And guys, the answer is this. What it actually looks like is this. What you basically have here is a salt crystal. Just like sodium chloride is NaCl, you've got a salt crystal that's copper sulfate. That's this. You've got coppers and you've got sulfates. But guys, the difference is that this crystal lattice is chock full of water. So guys, if you could imagine, it looks like this. It's like taking a salt crystal like NaCl and jamming this thing full of water molecules. Now guys, please understand, this does not mean that it's wet. What it means is when this crystal formed, water literally got trapped inside the crystal. And guys, this is what is called a hydrated crystal. And the way that we represent this is with the dot. So guys, that dot is telling you, here's the crystal, like CuSO4, but then the crystal is chocked full of water molecules. And in the case of the salt that you've got there in 1D, it goes like this. For every copper sulfate, for every atom of copper and every molecule of sulfate, you've got 5 water molecules. So guys, that's literally what's inside this flask. You've got this very clear crystalline blue stuff, but guys, there's 5 times as much water trapped inside this crystal as there is copper or sulfate. So there's all sorts of water trapped inside of here. So guys, how do we get the water out? And the answer is heat it. And when you heat this, the ionic bonds inside the copper sulfate break down and all the water goes away. And that's what this is representing. If you take this thing and heat it up, the bonds inside the copper sulfate break, the water goes away, and then the copper sulfate reforms in its dried out or dehydrated form. And guys, that's what this is talking about. So the bottom line is this. This is one reactant and this is 2 products. So when you write the Kc expression for this, the denominator in the Kc expression is actually just going to be CuSO4.5H2O. And that's the denominator of the Kc expression because that stuff on the left is one big reactant. It's just one compound. Because technically the water is kind of bonded to the copper sulfate. No, you actually, but the 5 does show up here. When you do the numerator, you'll have CuSO4, and then you've got the waters, and the water is where you see that 5. Yep, you got it. So guys, you now have the remainder of the day, more than half an hour, minus the fact that it is early out. But guys, you have the remainder of the day today to get this homework done. The answers will be posted on the wall. Guys, let's focus in and get this done. Then guys, when I see you next time, we'll go to lab and we'll muck around with Le Chatelier's principle. Then guys, we've got one more day of new material. We've got another lab and we're gonna take the unit test coming up pretty quick. So guys, let's focus in and get some good work done, and we will grade this next time. Go get them. Hey.
So, I'm having this meeting next week, the lab and the test.
Hold on just a second.